Okay. Oh, that's all right. At that one. Okay, so I guess I better sit closer. We're going to go through active circuits, analog, and then digital. And I also have a little addendum I did at the end of stuff that I didn't remember to talk about in part one. So let's see how it goes. We always have to talk about vacuum tubes because they're still around. There's questions on the exam about triode tubes and pentode tubes. And basically, it was the first sort of active device. Fleming invented what we today call a diode, where it could pass current from one element to the other in one direction only. And then later, I think it was Lee DeForest that added a control grid, and they discovered that by applying a voltage on the control grid, they could actually control the current flow. So that really became the first amplifier device, and also as a switch, well, mostly used as amplifiers. Today, most everything is based on semiconductor technology. And if you remember when we talked about the free electrons in material, the valence electrons that were on the outer shell that weren't tightly bound, they discovered that if they took a material like silicon, which is normally not a conductor, and they introduced some impurities, typically they use boron or phosphorus, they could create a material that had either excess holes or excess electrons. So it was either a positive charge or a negative charge. They discovered when they put two of these pieces together, a p-type and an n-type, it would act like a diode, just like in the Fleming valve, and it would conduct current in one direction from anode to cathode, the conventional current. The electron flow goes the other way, or charge flow. Because of that barrier between the two, there's a little bias voltage or an offset. There's another name for it, which I forgot at the moment. But typically, it's from 0.6 to 0.7 volts for silicon diodes and 0.3 for germanium diodes. Most diodes that you're going to run into are silicon-based. So everything is going to be in the actually 0.6 range. I think one of the exam questions is 0.7 volts. Most everything says 0.6, but the ARL is always right. What I did here was to simulate a typical 4001 diode, which is, I think, a 1 amp diode they use as a rectifier mostly. And this D2 is a perfect diode, the kind that don't exist, and plotted them. And you can see on the perfect diode, it started conducting here at 0 volts. And that slope of that line is just due to the 10 ohm resistor. If you see on the real diode, if you look down here, it's about 0.6 volts where that curve starts. And then the slope of the line is slightly less because you have some internal resistance in the diode in addition to the 10 ohms, which is why they're not perfectly parallel. Any questions so far? Okay. For people that aren't familiar, here's a collection of modern diodes, the symbols that are used to identify them on schematics, which are also exam questions, what they physically look like. So your standard diode is just a filled-in triangle with a line representing the cathode. On the physical device, not sure you can, well, on the second one, you can see there's a black stripe, and that's how they usually mark small diodes, with a stripe to indicate the cathode end. Some of the bigger ones tend to be bullet shaped, and the pointed end is the cathode. When we get down here to light emitting diodes, it's the same symbol with a couple little arrows indicating the light being emitted. There's a picture of a typical one. They come in almost any color you can think of today. We have photodiodes, which work just the opposite. So we have the light going into it, and they have a little window in the case so that light can get to the semiconductor wafer. It actually turns out that all the devices are photosensitive. And they discovered that, and they can enhance these so they're more sensitive. But if you could put the regular diode in a clear case, it would be affected by light. We have a Zener diode, which is another exam question. And they discovered that if you reverse the polarity on a diode, it won't conduct up till a point where you get a breakdown voltage. And they discovered by the way they make the material, they could control that breakdown voltage or the Zener effect. So they can do these at a whole range of voltages, 5, 10, 12, pretty much whatever you want, and use them as a simple voltage regulator with a resistor. You got Schottky, which has a lower voltage offset on it. And that's not a test question that I'm aware of. Nor tunnel diodes, the kind of special purpose. Laser diodes are used in a lot of things nowadays. They're about, the small ones like in the picture are usually about 5 milliwatts, and they can either be set to generate just a single dot, or with a little lens on there, they'll generate a line. So you can use them, like particularly in a laser cutter with a couple of those on there with a cross. You can actually, and on milling machines and other things, you can use them for alignment. There's a current regulator diode, which I don't have a clue what that is. Maybe Byron does. I've never seen it before.
No, I've never seen the symbol before.
Yeah. And then there's varactor diodes. Another behavior of diodes in the reverse direction is they have capacitance. And they discovered that the reverse bias voltage could control the amount of capacitance. So you can actually use it as a voltage controlled capacitor. And it's used for as a tuning element, or for FM generation as a reactance modulator, which we'll talk about later.
The definition of a current regulating diode is a device that maintains constant current flow despite voltage fluctuations.
Okay. Did you look that up or did you know that?
No, I looked it up.
Okay.
It's the
It's
power
not a test question, so, but it's good to know.
Wouldn't that be good for charging like lithium batteries?
Possibly.
Because they want constant current fluctuating voltage.
Okay. One of the primary uses of diodes is to convert AC to DC. So here I typical circuit with a 60 cycle, 60 hertz wave coming into the transformer. I think I set it up as a step down. I don't remember. Simple diode and a load resistor. And if we plot that, you'll see that the diode is conducting on the positive half cycles of the AC waveform. So what you get is what we call pulsing DC. If you filter that out with basically a low pass filter or integrator, you can smooth it and get almost a constant DC.
So the voltage will be the same through the diode. It'll come in at, let's say, 10 volts AC and come out 10 volts DC because it's only taking a half wave.
It's going to be less than the peak.
Okay.
In fact, it's going to be, well, it's going to be the square root of the peak or the RMS of this part squared plus the DC offset squared, whatever that is in this case. You don't need to know that, but it will be a lower voltage than you started with, definitely.
Okay.
Which is one of the reasons why we go to two diodes called full wave rectification. In this case, it requires a center tap transformer. So we conduct, or we get each waveform, each half, because these are 180 degrees out of phase. So in this case, you can see that the yellowish line is doing every half cycle. So there's twice as many pulses per second, so it's easier to smooth it out and filter it. Then we can go to a bridge rectifier because you can save money by not having to have a center tap transformer, which had to be twice the voltage. In this case, it's the same transformer we used in the first example with a half wave. And in this bridge rectifier, there's 4 diodes in a bridge formation. So you would have, if I can draw it right, one like this. One like that. And these would just be the opposite. I think I'm doing this right. Right?
Yeah. I think so. I haven't looked at a bridge rectifier schematic.
Yeah.
And
these come in a package already formed, so you don't have to, put 4 diodes together. Oops. And again, you get the same kind of every half cycle. Now, if you notice, there's a little more loss than there was on the full wave. because of the resistance in the diodes. And there's also, it's because of the range, it's hard to see the 0.6 volts, which would be down here to pass the threshold, which is why you see this little flat spot. That's because it's not turning on at 0 volts. Okay, so now that we got a diode, somebody decided, well, why don't we make it like a triode tube and add a third element? So if we take and put two N-type pieces of semiconductor material with a P-type in the middle, we have the diode plus another one, and it turns out that the current between the P-type and the N-type, which would be the emitter, and the P-type would be the gate, will control the current flow between the collector, which would be the other N, and the emitter, which is N on the opposite side. So it makes a little sandwich. Now, later they discovered that they could build a transistor that acted much more like a vacuum tube, in that they could control it with a voltage instead of a current by creating an electrostatic field, which would have sort of a pinch effect and control the amount of current flow. Here's an example of what we call a bipolar, which uses current as its control mechanism. And as you can see here, the P element is the base, and we apply a current through there between the base and the emitter. And that creates a current flow, or allows a current flow between the collector and emitter. And it's proportional to the amount of current going from base to emitter. But there's a gain factor of 100, 200, something like that. And that's what we use to make an amplifier, take advantage of that gain. The symbol for a standard bipolar transistor is over here on the left-hand side, showing the base, emitter, and collector. They tend to make, when they produce these, they're not symmetrical. And if I remember right, the emitter portion is larger than the collector portion, so it's not symmetrical. Point that out because when we do a field effect transistor, they are symmetrical, and it doesn't really matter whether you switch the source and drain around. They work the same way. So on a radio, the gain knob, is that what's controlling the current through the transistor? Maybe not directly, but yes.
Okay. So voodoo cells basically work on a bipolar junction, if I'm
right
correctly.
Yes. Here I'm just showing a typical sort of test circuit for a bipolar transistor. And you normally, in the data sheets for transistors, you will see a plot like this where they vary the current through the base at specific points and show what the voltage is across collector to emitter, so that you can figure out how you want to bias it, so you can kind of determine what voltage you want to operate at, how much current you want to pass through it, and then you pick your load resistor, which is this line here, and the slope of that's the value of the resistor. So normally for like a Class A amplifier, you would want to bias it so that it's normally operating with no signal right here in the middle, in between what we call the cutoff and the saturation. And cutoff means that at that amount of input current on the base, there's no current flowing from collector to emitter. In saturation, you've got the maximum amount of current flowing. So there's very little resistance between collector and emitter. And when you're actually using a transistor as a switch, you set it up so that the input current either puts it at this point or this point, off or on. I did a simulation of a typical 3904 NPN transistor. It's a very common one. It's used in all sorts of stuff, been around for years. And you can see the blue line is the collector current, and the yellow line is the gate. Oh, I got a G there. Should have been the base current. And the scales are opposite sides. So at the cutoff point, we've got 0 amps flowing on the collector. At saturation, it's up here at 10 milliamps, and that's limited by this 1K resistor across the 10 ohms, 10 volt source. And you can see what the equivalent base current is at those points. And in this case, for saturation, it's about 70 microamps. So if you do that division, you can see what the gain is. The bottom plot is showing the voltage versus the base current and how it goes from when the transistor's off, you've got 10 volts, and when it's on, you're almost down to 0 volts. Won't quite be there because there is some internal resistance. Okay, the next type is the field effect. It still uses the doped N and P material, but it adds another element which is insulated from the body so that we can create an electrostatic field across this material. Around here. And by making that a negative voltage across there, you can pinch off the current flow from the drain to the source or source to the drain because they're really symmetrical. The typical symbols are over here on the left. The only real difference is the direction of the arrow. Now, there's also a bunch of other types like MOSFETs and variations of those, but they all work pretty much the same with a electrostatic field that controls the amount of current flow. There's a picture of typical transistors from power transistors, which are in these bigger, I believe that's a TO3 package. The smaller ones are typically in these little plastic, was that TO92, I think, if I recall. You see one of the, what do they call these? It's not exactly a flat pack, and it's not it's almost a surface mount. It's a little bit bigger than some of the really small ones. These with the tabs on them are also power transistors. And that's how they get the heat out. You attach that to some sort of heat sink because they do dissipate a lot of power unless they're in switching mode. Okay, so one of the basic building blocks that we need to build radios and transmitters and other electronic equipment is an amplifier. So we either use a transistor or a vacuum tube or electron tube, or a valve, as they call it in England. And there's essentially four classes of amplifiers. A class A, which I talked about, where you would bias it in the midpoint, has the lowest efficiency, but it has the highest fidelity. In other words, it will almost 100% reproduce the input signal. But because of the low efficiency, it takes a lot more power and generates heat. They came up with a class B configuration, and it's normally two transistors, similar to when we saw the full wave rectifier, only with transistors. So each transistor will amplify one of the peaks, the positive peak or the negative peak. There's a little crossover because of the same 0.6 volts across the base to emitter, just like in a diode. So there's a little distortion, but it's much more efficient. Class C, they typically use in things like transmitters to get the efficiency. And it requires a tuned circuit on the output because it's only passing a portion of the peaks of the waveforms, and it requires the tuned circuit to resonate in order to sort of rebuild the AC wave. So it has to be tuned to the frequency that you're operating. And then there's class D, which some people call digital class. It's not really digital, but it does use sort of a digital technique in that you feed the analog signal in to a pulse width modulator. So you get square waves of varying width out of it, depending on the input voltage. And those are easy to amplify digitally, and then you run it through filters to get the audio frequency back. They typically only use these in lower frequency audio work.
About sticking bandpass filters on the end of it.
Low pass filter,
Okay.
low pass. We're not the filters yet. We'll talk about them. Okay, here's a class A that I threw together, and it actually seems to work. Been a long time since I designed an amplifier. It's set up for a gain of 6, and you can see the input waveform versus the output waveform. You notice there's a 180-degree phase shift, which is fairly typical, but there's no distortion that you can see. That's one of the advantages, and that's why you'll see Class A amplifiers in a transmitter for the audio section, for instance, before a speech compressor.
So distortion typically either shows up as ripple or clipping.
Yeah. And I have the thing to talk about the effect of clipping coming up.
Okay.
But in this circuit, basically you're using the R2, R3, and R4 network to establish the bias point, which is about in the middle, which would be around 6 volts. And you normally use a little emitter resistor that helps stabilize it. It does a offset voltage. That's a pretty standard configuration. It's one of the things I learned in college decades and decades ago. Now we're going to do the same thing with a junction FET. And the only real difference is the way you bias it. And the fact that you've got to make it go negative in order to turn it off. We still have the phase inversion between the input and the output, but it's a class A and we still get high fidelity. I believe one of the test questions on the exam is about how well it represents the input for a class A amplifier. Okay, now we hadn't talked about these, but this is just a package of a number of transistors, and we call it an operational amplifier. It's a differential amplifier. So any signal between this plus and minus input gets amplified by maybe a factor of 10,000. So it takes essentially, 0 volts between these two to generate an output. So if you use a feedback loop, and you have a voltage divider at this point, which will establish the gain. In this case, the 10 and the 2 is a third of the total value. So the gain would be 3. Okay. 20 and 10 is 30 ohms. And we're at 10 ohms. So we're 1/3 of the divider. Okay. So if I've got 1 volt coming in here on the input, when this output gets up to 3 volts, I'll have 1 volt on this side and they'll be balanced again. So the thing about dealing with operational amplifiers is you assume that both of these are 0 volts or virtual ground. And it makes it fairly easy to figure out the feedback resistor. And again, here's just a plot showing. Now, in this case, because we came in on the positive input, there's no phase shift. So this is a non-inverting amplifier. You could do the same thing by coming in on the negative side and make it an inverting amplifier. Okay, the next block are oscillators. We have fixed frequency, usually a crystal control or a packaged one where we can generate, in a lot of cases, it'll output sine wave, triangle, sawtooth, and square all at the same time. Or it can be an LC or an RC feedback network to generate a fixed frequency, where neither of these are variable. We have variable frequency oscillators, usually in a tuning circuit for a transmitter or a receiver. And there we have either an LC circuit with usually a variable capacitor. It's harder to vary the inductor, so it's a lot easier to get a variable capacitor. And you can use things like varactor diodes, which are even smaller, and you don't have a physical capacitor with plates that you got to turn and a mechanical thing. And the newer ones, we have direct digital synthesized, which uses some digital techniques to actually generate a sine wave by referencing a sine wave stored in a fixed memory, all the different samples of a sine wave. So you just look those up and output them and then filter it with a low pass filter again. And then digital clock signal generators, which is usually a crystal controlled oscillator. And they're normally, they come in small packages where you just supply usually 5 volts to it and you get a signal out of it. To make an oscillator oscillate, there's this thing called the Barkhausen criteria. You don't need to know that. It basically says for it to oscillate and maintain oscillation, you have to have an overall loop gain of 1. Okay, so it means you have to compensate for any losses in the feedback network with enough gain in the amplifier so that the overall gain is 1. Now, in order to start oscillation, you've got to have higher gain for it to actually start. But if it maintains higher gain, it will stop. I proved that many times in my simulator and trying to get an oscillator to oscillate. Here's an example of what they call a twin T. It's using 2 different phase shift networks, a low pass and a high pass, to generate the feedback. And I'm not sure in this one, other than I think it's this capacitor here that actually allows it to start oscillating, because it acts differently once it's charged up than when it first starts. But as you can see in the simulator, it actually started and oscillated. I had many attempts where I couldn't get it to oscillate. We can do the same thing with our operational amplifier. In this case, one of the little nonlinear elements is a little light bulb, a little pilot light, because it has variable resistance. So it changes the feedback gain. It does not do a sine wave. It's not exactly a triangle wave either, because you get a little rounding, but it's probably because I have too much gain in there. The other thing we can do is buy a thing called a monostable or astable multivibrator. The typical one you see is a 555 or some variant of it. And it works by charging up this capacitor that you add through this resistor network that you add, which gives you a RC time constant. So however long it takes to charge this capacitor affects the period of the waveform. So, and it's set internally with the trigger value. So as it starts charging up, when it gets up to the trigger point, it discharges it and then starts all over again if you configure it as a astable multivibrator. They can also be configured as what we call a one-shot, a monostable, where it will just produce one pulse every time you trigger it. And the width of the pulse is again going to be determined by this RC network connected. Okay, so we got amplifiers, we got oscillators, need to do something with them. So we can convey information on a waveform by what we call modulation. If you just have an oscillator connected up, as part of your transmitter to the power amplifier, putting out a carrier, people will see the carrier, but there's no information transmitted. Until you go to CW and you turn the carrier on and off, and then you can do Morse code. One of the basic forms of modulation is amplitude modulation, where we change the amplitude of that carrier signal. Now, you did it by off and on with CW. In normal AM modulation, you're using an audio signal to modulate it, or change the envelope of the carrier wave, which you'll see in a minute. And then we also have single sideband, which is a special case of AM modulation, where we only transmit one sideband of the signal. When you generate AM, you get, if you look in the frequency spectrum, frequency domain, you're going to see the carrier, and you're going to see an upper and a lower sideband, which are the audio signals offset in frequency. So they're one above and one below the carrier. To do single sideband, you eliminate the carrier and you eliminate one of those sidebands. So you're only going to transmit the baseband signal shifted up in frequency. So you have more power in that small amount of the waveform, because you're not using power to generate the carrier or the lower sideband, which is a duplicate. It's just reverse frequency. It's a mirror image. Next, we have frequency modulation, where we shift the frequency with the modulating signal, usually audio, but it can be digital. And in the case of a lot of the digital signals, what we call is frequency shift keying, where it will go into frequency steps. And we have phase modulation, which is very similar to frequency, except we're only changing the phase of the signal. It's one of those things, it's used for some of the digital modes. The human ear can't tell the difference between phase and frequency. We're not sensitive to phase. And then we have spread spectrum, which is what your cell phone uses, or radio control, the modern radio control, because it's very immune to interference from other signals. This is what a typical amplitude modulation looks like, where we have the message or incoming signal, which is, in this case, a sine wave, a carrier signal, and when the two are mixed together with a modulator, then we see the carrier signal increasing in amplitude and decreasing in amplitude proportional to the input signal.
In single sideband operation, it doesn't matter whether you're high or low.
It's just that they're different frequencies. Yeah. But the same information is there. Now there's a convention that you use lower sideband below
30 meters.
30 meters and upper sideband above, unless you're doing digital and you use upper sideband everywhere in digital mode. There's probably other exceptions, but it's not a law. It's a convention. You could do lower sideband on 10 meters, I suppose.
Yeah.
You may not find anybody.
Same thing with band plans.
Yeah. Well, except for the limits.
Yeah.
I think those are enforced.
But if you want to do, slow scan TV at the top of the band, the band plans are generally nationwide in most cases. In some cases, you will have local or regional band plans. The ATV group, LESAS, has had to make some adjustments because ATV repeater frequency is close to the struck frequency on rockets. But that has changed more because more of that is automated. So there was some, power limiting going on to make sure there wasn't any, interference there.
Okay, so if we look at in this case, a single sideband, well, it's actually showing AM and single sideband. In the frequency domain, we'll see our carrier frequency. And in the case of single sideband, it's suppressed carrier, which means it's filtered out almost completely. There might be some residual. And then we filter out one of the sidebands. So if we're sending upper sideband on single sideband, then we'd filter out the lower sideband. And we do that with either low pass or high pass filters or a band pass filter, and some other techniques to kind of separate them so that you can actually filter it. But for straight AM, you're going to get both sidebands plus the carrier. Okay, in frequency modulation, it's the same effect except for frequency. So you can see where the amplitude of the input signal is increasing, the frequency increases, and as it decreases, so does the frequency. And normally these are offset. You'd offset your modulating wave in order to get it to work properly. Now, phase modulation. This is the only one of these I could find. I'm not exactly sure that's a good representation because it seems it should be more proportional, but the effect is that you change the phase of the waveform with the amplitude of the input signal.
That's where you get your powered microphones. Yeah, the effect you get if you have one of those microphones that has a variable power signal on it.
No, I don't think so. No, because this is just doing phase modulation of the carrier. So you're changing the phase of the oscillator, with something like similar to FM with a reactance modulator, where it can change the phase. I can't say that I know a whole lot more about that. I've never tried to make one or analyzed it, but that's what they tell me. You won't see that too much and have to deal with it. I don't think there's any test questions on any of the exams other than maybe regarding PSK, phase shift keying, which is a little bit different. You're changing the phase, but you're in a digital mode and you're doing it in discrete steps as ones and zeros. Okay. One of the digital, or a lot of the digital modes use frequency shift keying, which is a form of FM, where in the simpler ones, they use what we call mark and space in order to indicate like a 1 and a 0 or a true and a false, but that's how we send data. So, and I don't remember the frequencies right now, but for some of the FSK modes, the simpler ones, there's two different I don't remember what they are.
1,000 hertz and 1,500 hertz are pretty common.
Okay.
Center frequencies.
So you're just shifting that in order to convey a 1 or a 0, what they call a marker or space. Another test question. Okay. Here I tried to set up showing modulation and demodulation. So I did a simple AM modulator because they're easy. And for a demodulator, this is what's called an envelope detector, and it's just a diode going into a low-pass filter. And what it will do is reconstruct the envelope of the carrier wave, which is your audio frequency in. This is the modulated wave, and this is what comes out of the envelope detector. which looks just like that. AM is easy.
Hmm.
Single sideband's a little harder because of the filtering required. Okay, the next thing is a mixer. In order to actually do the modulation or demodulation, and a lot of times you'll need what's called a mixer, a frequency mixer. They can be unbalanced or balanced. An unbalanced mixer will give you the sum and difference of the two frequencies, usually what we call the signal and the local oscillator or carrier, and you'll get two frequencies plus the carrier. If it's a balanced mixer, like a diode ring, you eliminate the carrier, it cancels out. So you just see the two sidebands. So that's why you use double and triple balanced mixers to do single sideband. It gets rid of the carrier for you. One less thing to filter. This is a simple little diode ring mixer I built. And there's the input waveform, there's the carrier, here's the modulated output. Now, this simulator doesn't have a way to show stuff in the frequency domain like spectrum, so I can't show the fact that it doesn't have a carrier and just has two sidebands. And there's no way to tell from this envelope. Now we use them to do what's called down conversion or up conversion. If we're doing down conversion, then the intermediate frequency that we're going to get out, okay, is going to be the local oscillator frequency, which is one of the inputs, minus the RF signal on one of the inputs, okay? So we'll put these two together, and the difference is going to be this intermediate frequency way down here. Now, if this was broadcast AM, these would set up where this would be at 455 kilohertz normally in an AM radio. So the difference in frequency between these two is going to be 455. So even though the RF signal is going to be somewhere between 550 and 1700 kilohertz, I think it's the AM band. So the local oscillator is going to tune to 455 kilohertz, one side or the other of your input frequency, depending on whether you want to get it up or low. For up conversion, we've got an RF signal out. That's what we want to produce. So this is what you would do in a transmitter. We have the IF frequency and the local oscillator. Okay, so we're going to take the sum and the difference of the local oscillator and the IF input frequency and generate these two sidebands on either side of the local oscillator. So in this effect, from a transmitter standpoint, this would be your carrier if you don't do anything else to it, plus the two sidebands. So that would be an AM signal. You don't have to know all those details for the exams, just kind of how it works.
Right.
Okay.
Photographic memory.
Well, you need the concept. And the fact that mixers typically do sum and difference.
When I learned back in the 72.
Oh,
Now, it's probably more detail.
Yeah,
we had transistors then. Mhm. But I only had one communications course taught by an ex-Texas Instrument guy. It didn't go well. Our first exam high score was 30. Okay. Okay, filters. Okay, we have essentially four kinds of filters: low pass, high pass, band pass, and band reject or notch filters. Low pass will pass signals below the cutoff frequency. In other words, it attenuates or filters out any frequency above the cutoff frequency, which is the half power or 3 dB point for attenuation for the filter. High pass is sort of the opposite. It attenuates signals below its cutoff frequency. A band pass is basically a combination of a high pass and a low pass, so that you can attenuate everything above or below the band that you're looking for. And then a band reject is sort of the inverse or reciprocal of the band pass. You want to block out everything in a narrow band, which is why they normally call it a notch filter. So a lot of receivers will have a notch filter that you can move around to block a particular signal that might be interfering.
Oh,
Yeah, I was wondering why you would use that.
yeah, I was too.
I was looking at, a detector actually works a little bit like a band reject. And it's amplification, because I was for a long time under the assumption that the circuit current going around the LC circuit was being amplified, by going through, but it's actually the rejected portion in the LC circuit that's amplified. So it's that tune rejection that gets amplified.
Okay, here's a simple low pass filter, which is just a resistor and a capacitor. What it looks like when you plot it in the frequency domain. And the point I marked here is the cutoff frequency. It is right around 100 kilohertz, which I think is what I picked these for. And you can see that, the slope goes down at, because we're plotting this in voltage, it's going to be 20 dB per decade or 6 dB per octave. Those aren't an exam, but that's what we learned. And also you can see that there's a phase shift through there of 90 degrees. And it is a minus 90. If you remember when we did the resistor and capacitor charging and discharging and how they work differently with one, the voltage led the current, or the voltage lagged the current, depending on whether it was capacitor or inductor. That's where this phase shift comes from. Okay, a high pass filter, we sort of switch places with the capacitor and the inductor and the resistor. Now you could make these with inductors and resistors. You just do them the opposite again. In other words, for a high pass filter using a resistor and inductor, the resistor would be in place of the capacitor and the inductor would be in place of the resistor. And we plot it again in the frequency domain. You can see the cutoff point should be another 100 kilohertz, and it goes down at the same slope because it's a first order filter. It means there's one nonlinear element, frequency dependent element. you got phase shift again, okay, in the opposite direction. We're having a 90-degree phase difference in the positive direction as it rejects. Now here I just took the two, offset them a little, frequency-wise a little bit, to make a bandpass filter. It's not a very good filter, but it does have a small pass band here where there's minimal attenuation of the signal, and you've got the same slope of 20 dB per octave. And in this case, you see that you got 180-degree phase shift change due to the low pass and the high pass filter effects. Okay. This is an example of getting serious about a filter. And this is a, what is that? A fifth order Chebyshev. And you can see that, you know, we have a very flat pass band. And even though these are not to the same scale, these slopes, the skirts, which is what they call these, are much steeper, I should say. You see, we're 50 dB down at these 2 points. We never got 50 dB on the other plots, but it takes a lot of components. And you can go up, I've seen 11th order.
And what's the loss on the fifth order?
Well, actually, I don't know.
Worse than 3 dB?
Probably. I would guess 5 to 10, but it's hard to tell from the scale. Because, I mean, there's no way to make up the loss. So you've got, in the real world, every one of these elements, particularly the capacitors, when you're in the passband,
So when you design your circuit,
are going to have some resistance and loss.
so when you design your circuit, you want to amplify first before you go
Or both,
before and after. Yeah,
because you can only amplify so much without causing a problem. So
Yeah.
sometimes
Yeah.
it's better to do both ends.
yeah. You may have to do both ends.
Now, here's an example of our old operational amplifier, because you can do anything with an operational amplifier. So you can make band pass, high pass, low pass. You could even do a notch or band reject filter. And all you're doing is putting either a high pass or low pass feedback network around the operational amplifier. You get similar results. They look slightly different, but the scale isn't the same. And in this case, we have a very narrow bandpass. I could have probably picked some better values.
Be good for tuning in CW or digital.
Yeah, probably good for both of those. Okay, so we got all the pieces, so we can build a receiver. Typically, receivers, older ones, and even it's come back, are direct conversion, where you can go directly from the RF signal to the audio signal. Tuned RF receivers were popular way back when, where you actually had a front end with 2, 3, 4 stages of RF amplifier that were tuned amplifiers at a frequency. that was mechanical issues, which is why they kind of went away. Then came the super heterodyne, where you started using mixers to change frequencies to generate an intermediate frequency that was usually a much lower frequency, so that it was easier to filter, just from a component standpoint. And then on modern radios, a lot of them are either totally or partially what we call a software-defined radio. And all of the mixing, filtering, even the oscillators are essentially done in digital logic, mathematics.
I remember seeing a guy out near the St. Johns River. He was evidently doing extremely low frequency.
You know what?
Yeah. He had a big long wire up with the weather balloon. Had a I guess it was a variable capacitor made by winding coils around a plastic 55-gallon drum and having some sort of deal in it. And, you know, he just had a crystal headset, and one side was fed by his antenna and the other side went to a ground rod.
Talking to submarines?
Yeah. Whales. Yeah, whales.
Yeah, I remember building crystal radios with a razor blade and a safety pin, coil of wire. And you could actually hear the local stations. Of course, you know, they were 100,000 watts. Okay, so here's an example of a direct conversion receiver. We have a low noise amplifier on the front end. It's not actually required. So the RF signal is coming into a mixer where we have an oscillator to tune it to whatever frequency we want and generate an intermediate frequency signal that we run through a low pass filter, essentially envelope detector. So we're going to get the envelope waveform out, which is what we call baseband. That was the originating modulating signal. So they're very simple. They're not the greatest radios, but they're simple. You can do one with a handful of parts. Here's a tuned radio frequency one, where you have all these front ends where you've got resonance circuits that you tune for the frequency you're looking for, with amplifiers on each stage, so that you get a much amplified RF signal when you go into the demodulator.
Some of the crystal radios do that, you know, with passive circuits.
And in this case, can be just a simple diode detector with an audio amplifier. And those were big back when I was growing up.
Ooh.
I don't know. I've seen one in real life anymore. Okay, then we got most of the radios in modern times are some version of a super heterodyne. This is a typical example where you had sometimes a pre-selector, which would be a bandpass filter on the front end through an RF amplifier, another pre-selector that's also selected with the front end one, going into a mixer. And these are just to get rid of out of band signals that you don't want. They're using an LC filter. I'm not sure what the crystal there, but I guess they're able to tune it slightly and generate this IF signal. Usually, this IF strip will have filters and amplifiers in it. And that's where you do most of the amplification of your signal and through the bandpass. Depending on whether you're receiving AM, single sideband, CW, will determine the type of bandpass filter, or whether it's very narrow. In fact, if this was receiving digital, like FT8, it only needs to be 50 hertz wide. If it was CW, it'd be 150 hertz. If it was SSB, it's what, 2.5 kilohertz or 1.5?
Yeah, 2.5.
2.5.
Yeah.
And then for regular broadcast AM, it's going to be up, what, 6. And then if it happened, well, this isn't an FM, but in FM, it's much wider bandwidth. Was it 12 or 25?
I think it's 12. That may be the amateur. Is 12 to 15, I think.
Yeah.
The commercials, 25.
And then we're coming through a second mixer to reduce the frequency down, and then selecting one of three in this case, one of three different types of detectors, because we do them slightly different, or whether it's an AM signal, a single sideband, or a CW signal. And these are all at 455 kilohertz. So these would be different bandwidths on these selections. Another amplifier, and then the detector, and they're not showing it, but an audio amplifier on the end. Okay, for a software-defined radio, this is a fairly typical one. In fact, this is a diagram out of my 7300 ICOM radio. And you notice these dashed red lines. Those are two integrated circuits. So all of that is taking place in two integrated circuits.
I remember back in the early 2000s, I was looking at some of that stuff, and people were home brewing using graphics cards.
The DSPs pushed them out.
Yeah,
Yeah, because they had high-speed A to Ds.
yeah.
And essentially, that's what you do in here. Now, this has got the analog to digital converter before this first chip with all the mixers in it. So you're taking the analog RF signal, and this attenuator box is also a preamplifier. Can do both depending on the feedback from the AGC. And you can externally select different attenuation or preamplification. So you send the RF signal into an analog to digital converter. So from this point, you're strictly dealing with digital samples of that signal. So if you want to amplify it, you got a sample that, say, is 5. You multiply 5 by 2. Now it's 10. I've got a gain of 2. It's this simple digital multiplication. And the same thing for the filtering. You use, it's slightly more than multiplication, but it's just mathematics that you're doing digitally.
Well, the beauty of the digital is you're not having the losses,
Right.
through your filters.
And you can make filters that look like square wave. So, and you're sort of doing the same type of things you do in a super heterodyne. It's just that you're doing it digitally. Then you come out in the second chip where you're doing the IF to AF portion of the signal through bandpass filter, amplifiers, your detector circuit, depending on whether you're doing AM, FM, sideband, any of the other modes. It will be done in this circuit with changing parameters from software. And then a digital to analog converter to get it back to an analog signal again. Okay, so we can also make a transmitter with the same components. Either AM, single sideband, FM, or digital data doing any of these digital modes. These are sort of the most common ones today. FT8 is probably the most common in use today.
What's that?
FT8 is a
Spin off of JT65.
no. There's a guy, Joe Taylor, who's a physicist that did research on deep space communications, weak signal, and he developed protocols for transmitting and receiving weak signals from, planetary stuff and beyond. And they adapted that to amateur radio because he's also a ham. And he has this software package called WSJTX for weak signal Joe Taylor X. It has a suite of protocols, FT4 and FT8. What is it? JT9. I think 65 is in there. There's a handful of them, and they all work on weak signal, which means they can pick signals that are, I've got signals 20 dB below the noise level and decoded them. Huh? Well, it looks like it. You won't even, if you look at the spectrum, you won't even hardly see a bump.
Some of these modes, you can lose 80% of the signal, 90% of the signal, and it can actually restore the full message. Yeah.
And one of the, like an FT8, the reason there's an 8, because there's also FT4. FT8 uses 8 audio tones to represent the digital word. So in essence, it can send 3 bits at a time, because 3 bits represent 8 values. So each one of those tones is one of the 8 values. So it's very efficient. Now, I think there's a mode, I don't remember what it is, that actually uses 16 tones. So you're doing 4 bits at a time.
Sounds like MFSK, maybe.
Yeah, I think it's that one. Okay, so for a simple AM transmitter, we sort of reversing things, and we've got an oscillator, which is going to be our carrier frequency. And we bring in the audio signal, amplify it. Maybe we compress it, do some manipulations with it. Run it through the modulator, which is another mixer, and then run it through a power amplifier and a low pass filter just to get rid of any high frequency harmonics that we don't want. It's pretty straightforward. AM transmitters are easy. Easier than a receiver. Now for an SSB transmitter, we have to do sort of the same thing, but we got to get rid of the carrier and we got to get rid of a sideband. So that's basically the difference, is we're using the balance modulator. So that got rid of the carrier. We filter out one of the sidebands. And in this case, we're running it up through another local oscillator and mixer to upshift it to a higher frequency and then outputting it. I actually don't understand why we don't get two sidebands again, or is one so far up that we block it out when we do this?
It's all magic to me.
That's why-
I mean, there's got to be a second product from that mixing, but it's going to be displayed. Well, depending on the difference in these frequencies, it's going to be displaced pretty far. So you probably take care of it with that low pass filter that they're not showing in this block diagram.
That shows up on your neighbor's TV.
Well, then you have to go be nice to your neighbor and see whether or not it's your fault or their fault. There's stuff on the test about that. Okay, for an FM transmitter, again, we start with the carrier oscillator. We have the audio input going to a reactance modulator, okay, which could be a varactor diode because it can change reactance with the voltage. So that's how we change the frequency, because we can change the reactance of part of the tuned circuit. Just an amplifier. Now we have a frequency multiplier. We hadn't talked about those. Frequency multiplier is just a tuned amplifier that is tuned to harmonic frequency. So if I had, say I had a 1 megahertz signal coming in, this multiplier, if it was a 2 times multiplier, that's typically, sometimes you see 3, it would be a tuned RF amplifier for 2 megahertz. So it would see the harmonic of the input and amplify it and pass it on. And then we might do it again to get a frequency multiplication of 4 or a times 3. So you can see 2, 4, 6 a lot of times in FM transmitters to multiply the frequency up to where you want it, because you're at a much lower frequency where you start. And then just through a power amplifier. So the basic difference are the frequency multipliers, which are normally used, and the reactance modulator. Okay. We're getting up to Viron's area. Antennas. So we got transmitters and receivers. So we need to connect them to something. So we have what they call the isotropic radiator, which is the theoretical antenna that you measure other antennas against as a reference. The isotropic would generate a spherical radiation pattern in all directions. You can't build one. I'm not sure that I guess the end of a wire might be sort of close, but it's basically a reference. And we reference other antennas to it in decibels relative to an isotropic. That's dBi. Okay. You'll see here when we talk about half-wave dipoles, sometimes they'll reference it to the half-wave and it'll be a decibel relative to a dipole or a dBd. So one of the simplest, what you see on AM broadcast stations are quarter wave vertical antennas. On AM broadcast, because of the frequency, they're down at what, 160 or below meters?
What,
AM broadcast?
Yeah.
They're very high antennas. But they use verticals because they're omnidirectional. And they want to send their signal out, they broadcast it to everybody. So that's why they don't use beam antennas.
That's maybe it's Voice of America or someone like that.
Next is most common probably in ham radio is half-wave dipoles or variations of a half-wave dipole. Dipole means there's two poles. It's got two elements that are basically opposite polarities of the signal. Sometimes use it as a reference, DBD. It's claimed to be 2.15 dBi more than an isotropic. That's theoretical. Now, because of ground reflection, it's actually more like 6 dB. Unless, of course, you've got a half-wave dipole in free space, which means, miles up in the air. And then it's only 2.15 because there is no ground reflection. But nobody has a half-wave dipole in free space.
I didn't realize that the ground reflection gain was that much. That's a lot.
I just watched the Dave Castor video on that. And he showed a bunch of examples that he modeled, and it was anywhere from, depending on height to the ground and inverted, anywhere from 5 to 6 dB.
So inverted this way? Or?
No, inverted V.
Yeah, okay.
Was less, but not that much. That was the
Yeah.
thing he did. He did it even 60 degrees,
Okay.
which you're not supposed to do.
Yeah.
And it was still only maybe a dB and a half less than the straight wire half wave.
Interesting.
It was surprising. Said it surprised him. Okay. And he's been teaching this stuff for years and years. The half-wave dipole, there's kind of three variations. The normal one you see is center fed, where the elements are equal quarter wave lengths. There's an off-center feed. The antenna is still half wavelength long, but you feed it at 20, 30% from one end. It varies. There's different, you get a different impedance match depending on exactly what point you pick.
And the difference between the off-center fed and center fed and in fed is what harmonics it'll operate on. So if you have a center fed, I believe it operates on even harmonics.
Right.
If it's off center fed, it operates on odd harmonics. If it's in fed, it works on all harmonics. All harmonics.
Yeah, that's one of the benefits of an in-fed is you don't have to do a lot of traps and other things. You can pick up, if you had it 80 meter in-fed, which would be 3.5 megahertz, you're going to get 7 megahertz, 10 megahertz, whatever, 4 times 3.5, on up in 3.5 megahertz.
If you do an 80 meter 210 in-fed, you've got all the bands without a tuner above 80 meters.
That's what I had before.
Yeah.
I'm about to put one up and see. I have a center fed fan dipole right now that definitely is more than 6 dB greater than my vertical.
In some directions.
Yeah, but it seems to be all directions. Remember, I'm probably more closer to 90-degree inverted V.
Mm-hmm.
So it's fairly omnidirectional. It's slightly oblong. And because it's pointed a little bit east of north, I get sort of over the pole stuff, and Europe is a piece of cake.
Well, I was thinking of as far as your low angle radiation, within maybe 1,000 miles, your band dipole is going to do the majority of the work. But for further than that, your vertical may be doing the job better, but only you would know because you see the signals.
Well, I can switch back and forth on
Yeah.
FT8 and it does better on everything.
Really?
Really.
Okay.
I'm thinking about taking the vertical down, putting
Yeah.
something else up.
Yeah, it's not doing you well.
Okay, and then we have beams, which are sort of modifications of half-wave dipoles. The most popular is a Yagi Uda, named after the two Japanese guys that invented it. As I understand the story, it was actually Professor Uda that did the work, but he worked for Yagi. So Yagi got first name.
Yeah.
Then there's the log periodic, which is similar but different. And then there's quad antennas, which are loops,
Well, the log periodic is your typical, TV.
antenna. The beams have high gain and narrow bandwidth. So it's just a compromise of the more gain that you want to try to get out of an antenna by squeezing the radiation pattern, the narrower the bandwidth is going to be.
The quad gives you a little bit more gain than the Yagi. And the reason for that is that you're working with, a half wave radiator, with the Yagi, and with the quad, you're working with a full wave loop. So, but after probably about 7 or 8 elements, the difference.
Yes, diminishing returns.
Yeah.
Actually, they claim it's probably not worth it after 5.
Yeah.
You're better off stacking them, and you get 3 dB by putting 2 of them up. And it takes probably 10, 12 elements to get that 3 dB just by adding them. And plus, you get a very long boom. Or you can even put 4 of them in a quad array, get 12 dB increase over the total. Okay, quarter wave verticals work off of ground reflection. Normally, if it's just a straight quarter wave element up in the air, they use radials, which is just an array of wires insulated from the ground that reflects the signal, and that's where you get the gain, part of the gain, maybe as much as 3 dB or so due to that reflection.
There's some good studies on counterpoises versus radials. And usually a counterpoise, you can get better efficiency, than a ground radial system if it's a few wires that you're working with.
Because in essence, if you look at it like in this picture, it's a vertical half-wave dipole, but one of the elements is this imaginary element in the ground. So that's what you're going to reflect up. So the more efficient your radial or counterpoise is, now if it's just real high in the air, part of the shield of the feed cable could act as the counterpoise. So it could be your other element. Over here, some examples of different lengths, whether it's a quarter wave, a half wave, and so on, and what the radiation patterns look like. For a normal quarter wave vertical, this is a cross section of the vertical radiation pattern, because it's really just a torus donut sliced in half, because that's where the ground is. If it was in free space, it would be a complete donut. And as that gets longer, or more wavelength, you see how the pattern changes. We get a lower radiation angle by going to a half wave, and we go to 5/8 wave. It's lower yet, but we're starting to get these more vertical lobes. So part of your power is going out there. And then on 3/4 wave, you're mostly vertical. And then full wavelength. You got nice lobes, but very high radiation angle. Wouldn't be good for long distance. And then when you really get up there, then you just get this mess of stuff. Okay, here's a half-wave dipole showing kind of the radiation wave, which is partly showing the polarization. And you see that it's what we're sending is the E field. Okay, when you put a signal on the antenna, you actually generate an E field and an H field, the magnetic field, which will be perpendicular to the electrostatic field. What you normally are receiving and transmitting is the electrostatic field. So if you notice, it's varying along the element. So if that element is horizontal to the Earth, that's what we call horizontal polarization, because the waveform is varying horizontally. Even if you rotate this around to where, because this wave is all the way around it, even if it was shown vertical, it's still going back and forth in a horizontal direction. Right. If we rotate the antenna vertically, okay, now I've got that waveform going up and down vertically, even though it may be going all the way around 360, it's still vertical, so it's vertical polarization. A typical half-wave dipole in free space, which is higher than most people have one, is going to be 72 ohms. As it gets closer to the ground, the impedance lowers, or if you angle the elements down like an inverted V, you lower them even more, you may get down to 25 ohms. So the impedance is going to decrease as the height decreases. Test question. This is showing the free space radiation over on the right. You know, you got a big donut, and we have no radiation along the axis. So it's directional in that it's broadside to the wire or the element. And this on the left is a cross section of that, just showing the lobes.
And that,
Now that
that's your MF and HF, that's never really true. Because you still end up getting a little bit off the end.
yeah. Yeah, this theoretical stuff and the real stuff are close, but not the same. And as you get closer to the ground, this gets modified a lot. It's easier to show these nice symmetrical ones. Okay, we have an off-center feed, sometimes called a Wyndham.
Wyndham is usually, technically it's going to be a parallel bed off-center dipole.
What do you mean?
Parallel line like window line,
Oh,
ladder
okay.
line. And the third is,
Yeah.
classic Wyndham.
But it's still half wavelength long, and instead of in the center, you're feeding it at a point, from what I understand, in the 20 to 30% range. It varies depending on what impedance you want.
Flavor.
Kind of directional.
You get different harmonics than you do with the center fed,
And
and your impedance is easier to match because wherever they've done it here, they're saying it's 235 to 270. So with the right kind of balun, I can get close to 50 ohms. So I have a good match.
yeah, most of those will, if it's a 30%, they'll give you a 4-to-1 balance. If it's 20%, they'll give you 5-to-1 balance. And I think the only one who's really doing the 5-to-1 balance a lot is Chameleon.
But the benefit isn't directional, it's still omni.
Well, it's the same sort of pattern.
Yeah, the pattern then
It's broadside to the antenna. The radiation angle is going to be affected by how high it is off the ground. And for most of these, the optimum is half a wavelength.
I'm just trying to figure out why it's not in the center if it's not directional.
yeah,
Particularly in just.
Well, remember, your wave is still going to be resonating like that. Doesn't matter where you feed it.
at least on the lowest one.
Well, I mean, it affects the impedance and harmonics, and then your current is still going to be like that. So you got maximum current in the center. You have no current at the end because there's nowhere for it to flow except for end effect. But in theory, there's no current at the end.
I was trying to figure out why it wasn't.
So-
And when you feed it at the middle, which is the highest current point, that's going to be the lowest impedance.
So when you grab your antenna and the minimum RF burn, do you grab the middle or the end?
It's a good question because the end is very high voltage and no current until you grab it. And then I suspect the high voltage is going to create a current through you. And what they call an RF burn, which is bone deep. Okay. So when we have an end fed, we normally feed it with a balun or unun. I guess it's actually an unun because it isn't balanced. And it's still a half wavelength antenna. You're just feeding it different and you get different effects as far as the harmonics that it resonates at. And also the impedance is going to be very high. So you're going to use a 49 or 64 or something to one transformer. They'll be ununs technically because they're unbalanced to unbalanced.
You know, if you do a parallel fed wire, you know, ladder line or window line, loss from mismatch, you know, high SWR is very low. And so, you know, you can be very agile, frequency agile with the antenna, as long as you have a tuner that'll, you know, handle the mismatch.
Now, on this off center, if I pick my point, you know where my cursor went there, just right, I can get this to say 350 ohms impedance. So I could feed it with a 350 ohm twin lead.
Yeah.
It comes in 300, 450, 600. Yeah. And it's much lower loss than coax. Although you still have to have a matching transformer before you got to your receiver because you got to get it back to 50 ohms.
Yeah.
I've been for a while.
I've had fun with those.
Okay, the famous Yagi-Uda, it's a multi-element directional antenna. It consists of a driven element and usually only one reflector. And then additional, what we call directors. And the way it works, as I understand it, is you get a reflection of the signal from the driven element, and the spacing between these two is such that because there's a 180-degree phase shift on here. When it reflects back off of the reflector, at some point it comes in phase with the signal off the driven element, so it adds to it. So you get that portion of the wave reflected back, just like the same effect with the vertical and the ground reflection. It's the same kind of thing, and it adds to the signal. And it decreases the signal going this way in the reverse. So that's why you have a very small radiation lobe on the back end of a beam antenna. Then these additional driven elements are spaced such that they add more to it. And it's a very complicated formula, figuring the spacing for all of those and the length. In this, the driven element on the Yagi is going to be approximately a half a wavelength. The reflector is going to be 3 to 5% longer. And each one of the driven elements is going to be a few percentage less as you go down. Okay. Kind of like a log periodic where they get smaller as you get farther from the driven element. Here's what a radiation pattern for a Yagi looks like. So you see that we have very small side and rear lobes. They're in this chart. They didn't label it. Typically 20 dB down. And over on the right is an elevation pattern. And you can see it's a very low radiation takeoff angle, is what they call that. The blue lines are a dipole, a half-wave dipole at the same height, and what the difference in pattern would be. And you can see on the dipole, it's bidirectional. You don't have anything along the element, but broadside to it is where your maximum radiation is. And then we have a quad. And like Byron said, these are full wavelength loops. Now, they don't have to be square. They can actually be any shape. It just affects the polarization a little bit. But basically, where you feed it determines whether it's horizontal or vertical. If you feed it on the bottom, then it's horizontally polarized because most of your radiation is on the upper and lower elements. If you feed it on the side, it's vertically polarized. So if you were to make it, say, a rectangle, much taller than it was wide, and you fed it on the side, you'd have more aperture for a vertical radiator. A lot of times they'll be crossed and you'll see it as a diamond, but it's still sort of the vector thing. It's either horizontal or vertical, depending on which corner you feed it with. And we talked about polarization, where it's defined as the orientation of the E field with respect to the Earth. That's a test question. So if it's horizontal to the Earth, it's horizontally polarized. If it's vertical, it's vertical. If it's bounced off of the ionosphere, it's elliptical. If it comes from a satellite, it's probably circular. But we're not talking about those today.
Or if it's Nimbus, it's actually circular.
Yeah. Yeah, when you get to reflections,
Nimbus.
it changes.
You're vertical.
Yeah.
Oh,
Anytime it's reflected off of things, it affects the polarization. And then, of course, when you got a satellite, that's rotating, it's changing vertical, horizontal. So a lot of times for satellite antennas, they'll have crossed Yagis so they can receive it either way.
This is kind of off topic, but this 5G stuff that's going on, and then finally come out,
Yeah.
is that horizontal or vertical?
Most said I would imagine to be vertical, but
I think, although they're patch antennas, so I'm not sure. I don't know much about them. They're magic.
always
When you get into the gigahertz stuff, that's a whole different world.
the the weekly ham radio broadcast. What they're saying that they're doing regular cell phone 3G and 4G satellites that can pick up the cell phone,
Mm-hmm.
but they're arraying like 1,000 dipoles on the satellite. I'm thinking, how are they doing that?
It's small.
Yeah. It's all printed circuit boards. Yeah.
Yeah, when I was doing some consulting with the Air Force on some classified stuff, there was a radar system called flap lid. It was about 6-foot diameter circular platform that you could raise or rotate. In other words, azimuth elevation.
Yeah.
It had 1,024 dipoles on that were phased. So you could phase shift the beam depending on the phase shift to the antennas. We didn't make it, by the way. Okay, so we got transmitters, receivers, and antennas. We need to connect them with something. We call them feed lines. Most of the time we use coaxial cable. It's relatively cheap. It's common. It was invented to reduce interference from other signals because it maintains the electrostatic field within the cable between the center conductor and the shield. There's a number of variations. Amateur radio is almost all 50 ohm. TV would be 75 ohm. Occasionally, you might see that used as a matching transformer to an antenna, where you can do some magic quarter wave stuff and it matches most of these coax that's going to be used, like in your shack, is going to be RG58 or 8X, which are like 1/4-inch diameter. There's some other smaller ones. These are probably the most common. Probably 8X is becoming the most common because it's flexible, relatively cheap, it's easy to work, pretty good shielding. And if you're only doing short runs, you don't care about the loss that much.
I saw DX Engineering has a flexible LMR 240.
Okay.
And that's a little bit more efficient than the 8X. It's a little bit thinner.
And a little bit more expensive.
Yeah.
That's the other trade-off on all these things is cost versus. When you get into the 1/2-inch sizes, like RG8 and LMR 400, they're much stiffer cables. Even though there's an ultra-flex version of LMR 400 that uses stranded center conductor, so it's not quite as stiff. The straight LMR 400 is very stiff.
Yeah. And where does the 316 fall in between the 8U and the 400?
I believe the one that's missing off of my board.
Yeah.
Or no, that's 213 was the one that fell off.
213. Yeah.
I don't know if I had the other one up there or not. And the 6U and the 59 are the 75 ohm that you see in TV. Whoops. Then we also have 2-wire, where you have your normal TV twin lead, which is 300 ohms because of the separation. It's like a ½ inch. You have open wire, where you got 2 wires separated by spacers similar to this ladder line. And I think that's like 600, normally 600 ohm. You have window line, which isn't shown, and that's I believe like 350 or 450 range. It's like a wider twin lead with holes cut in it called windows.
Yeah, most of that I think is 450.
And they are lower loss than coax, but they do radiate and also pick up interference. So everything's a trade-off. Any questions? Discussions? What did we forget?
So I
think so.
question, when you put a mast up, so I'm assuming because we're in such a lightning prone area that you'd want to ground both the mast and use a lightning arrestor on the coax side, right?
Well, you normally put a lightning arrestor where your feed line, whatever it is, enters your shack, your radio room, whatever you call it, where your radio is. And you'll want to have a good ground system to connect that to, that's tied into your facility ground. And it's probably not going to be close. So you need to run a ground line from where your facility safety ground out by your service entrance is, and there'll be a ground rod there, and you need to connect that up with wherever your ground rod is, just outside your shack entrance. If you really want to do it right, if that's a long distance, you probably want to put another ground rod every 10 feet or so along the path, because the effective area of a ground rod is about 8-foot radius.
Okay.
So the more ground rods you have spaced that distance apart, the better connection to ground you have. And the ground we have around here, according to a chart I recently saw, we're somewhere between 4 and 8 on that chart, which is not great, but better than Colorado.
Also been fun with the train recently or not.
You can, if bringing the line down on your mast, you could put a lightning arrestor and a ground at the base and tie it to a ground rod at that point, particularly if it's a long distance from where your shack entrance is.
Okay.
Probably alleviate a little bit of the stray current if it caught most of it right there.
The other thing that's a good thing to do is get an antenna switch that, like the Alpha Delta, that shorts the connections out. So when you don't have one of the ports selected, they're grounded. So it would discharge, particularly with a vertical antenna. You could get some static buildup. And if that's connected directly to your radio, you could actually get enough static buildup to cause a problem. Whereas if you got it through a grounding switch, when you're not using it, you discharge the static to ground.
And if you're Dave Lorette, you have one at the bottom of the antenna. You have one at the where you enter the building, And then you have a restaurant also on the inside too. On your big, ground bus.
But also,
You'd have a halo on the top and bottom
It's all
too.
connected to your channel.
Yeah.
Every time you add,
also,
you're adding resistance.
okay,
Wide.
go ahead.
I'm saying if you add multiple arresters, aren't you adding resistance to the line?
No more than a connector, because all they are is, in most cases, it's some sort of spark gap, usually a little gas discharge tube. So there's no additional resistance other than like a barrel connector.
Okay.
So compared to the loss in the line, it's going to be fairly insignificant.
Got it.
However, it doesn't matter how many of them you have or where they're at. If you have a direct strike, all bets are off. So the lightning arresters and the grounding, help discharge potential lightning, which is the way, if you've seen a lot of the facilities that have lightning arresters on the peaks and the corners all tied together with grounds, those are to dissipate the charge before you actually get a lightning discharge. So they help, but they don't 100% prevent it.
Right. Okay. Thank you.
Did I answer your question?
You did.
So if you take a wiener and you wrap your ground wire around it, will you have a cooked wiener after the lightning strikes?
You may not.
Wrong.
Go ahead.
The weird thing, with lightning is that the stuff is polarized. If you'll notice, on the power poles, it's about 3 feet off the ground, they have a little loop coming out. And if you see something that's been damaged by lightning, like coax, you'll see holes, ever so far in the same polarized plane.
Everybody's back? Okay, we're going to talk about digital stuff. Digital logic circuits operate on two values: zeros and ones, trues and falses, offs and ons, highs and lows, all kinds of different term mark and space, which we talked about earlier. And that's how we represent decimal numbers. The binary numbering system is based on the powers of 2. So it's a base 2 system as opposed to our normal decimal base 10 system. So 2 to the 0th power is going to be equal to 1. 2 to the first power is 2. 2 to the second power is 4. On up the line, 2 to the 8th power is 256. Sometimes, because you'll see when we get a whole lot of ones and zeros, it's a little confusing. So we sometimes use octal base 8 or hexadecimal base 16 to represent the numbers, so it's a little easier to manipulate. You don't have all the ones and zeros. Here's a little chart showing for decimal numbers 0 through 10 what the binary representation is. And this is what you would call big Indian as opposed to little Indian, where the most significant bit is over here on the left and the least significant bit is on the right. And the other one is just the opposite. You go 2 to the 0, 2 to the 1, 2, 3. That became a problem in the computer world because some computers were built to big Indian, some were built to little Indian, So you had to be careful of reading the data to know which format it was in. The octal representation, we only need 2 digits to represent decimal values from 0 to 10. So we go up to 7. Okay, so that's the 8th value. And then we go to the next digit. So we go 7, 10, 11, 12. In the hexadecimal number system, we're going to go 0 through 9 and then start with A, B, C, D, E, F, and then go to the next digit.
We're doing on up to the 26th.
No, 16. So on the 17th, when you go to the next digit. So it'd be 1, 0, 0 in hex would be 17, I think. Okay. If we write logical expressions for binary, we use the and symbol, and usually in programming, most of the languages, it's going to be a double ampersand sign. In the case of an or function, it's going to be the double vertical lines, and I forgot what they're called.
Pipes.
Which pipes?
Pipes.
Well, they're pipes in Unix. I don't know what they're actually called on the keyboard, though.
Pipe.
Is it a pipe? All right. And then we use the exclamation to represent the not value. Yeah. So if you have a true and a true, the result is true. A true and a false, it's false. False and true is false, and false will be false. In the or function, true and a true is true, a true and a false is true, a true and a true, or another false and true. The only time it's false is when both inputs are false. You could have even 3 or 4 inputs. As long as they're all false, its output would be false. The not operator is just an inversion. So it's the opposite of whatever the input is. When we have that in hardware, it's going to be called an inverter. Okay, so we implement those things in hardware with gates. We have an inverter gate, an OR gate, or an AND gate. We also have the not versions of these, which would be a NOR gate or a NAND gate. So the truth tables, which are just little things to make it easier to see the function. In the inverter, it's just the output is the opposite of the input. In the OR gate, it's true unless all the inputs are false. In the AND gate, it's only true when all the inputs are true. If I had a NOR gate, it's going to be just the inverse. So the output's going to be true if both inputs are false. In a NAND gate, the output is going to be false when both inputs are true. Clear as a bell, right? Okay, so here's an example of an inverter where we're feeding it with a clock signal and the output is just the inverse of the clock. That's important in a lot of digital logic things because you want that inverse function. Here, I took an AND gate and an NAND gate, and we feed it with 2 signals and see the result. So the AND gate is true when both of the inputs are true, or equal to 0.3 in this case. or octal 3, or hexadecimal 3. The NAND gate only goes false when both inputs are true. So it's just the inversion of an AND gate. Clear? Okay, so I can take those gates and put them together to make another element we call a flip-flop. And there's several varieties of flip-flops. This is a D flip-flop. We just call them D-flops, which is kind of two purposes. It can act as a register to store a value, or it can be set up to toggle, which you use in a counter or something. So in this case, we're feeding a data pattern in at half of the clock rate. So it has two outputs, Q and not Q. One is the inverse of the other. So the Q output goes true when the data input is true and I have a rising edge of a clock. And obviously the not Q is just the opposite. When I have a 0 or a false on the data input and I have a rising edge clock, it's going to change the state back to a 0. So that's basically doing its register function. It's storing this value in here. And as long as that stayed true, the Q output would stay true. If we connected the input to the output, we can make it toggle so it will alternate.
Got that non-volatile.
This would be volatile memory. Yes, because it would lose its state as soon as you take power away. Here's a different version called a JK flip-flop. And it's maybe a little more versatile, where we have two inputs that determine how it operates. And in this case, with both the J and K inputs set true, it's going to act as a toggle. So it's going to change state on every clock pulse. So it's basically counting in binary. So it's dividing the clock by 2. So we now have a signal that's half the frequency of this frequency. So if this was a 1 megahertz clock signal, which showing what's coming out of it would be a 500 kilohertz square wave. If I fed it to another one, it's going to divide it by 2 again. Okay, here's how we can put them together to make a counter. In this case, it'll count up to 3 bits. So I'm not showing the clock coming in, but as it counts, okay, we start off with all the stages at 0. Okay, the first clock pulse that comes in is going to change the output of stage 1 to true, or a 1, leave the others unaffected. On the next clock pulse, the first stage is going to toggle back to a 0. The second stage is going to change state. So now we're up to binary 2. The next clock, I labeled that wrong. There should be a 1 here. The next clock would be a 3. And this one's also shifted. This should be a 1, 0, 0 for 4. Then we do a 5, a 6. And then on the last one, we're going to have 1, 1, 1. Well, I really screwed that one up. So that's how it would count 0 through 7, or 8 steps and then start over again.
See if we were paying attention.
Yeah, see if they're paying attention.
It's a feature.
I guess I did that very late at night.
Got to switch from decap.
Okay. Now we also can do shift registers where we're going to take a value and shift it through. So in this case, we're going to start off with this value being a 1 because it's a NOR gate and all of these are at 0. So the output of this would be 1 if these are all 0. So the first clock is going to come in and the first stage is going to go true. The next clock, it's going to shift to this stage. The next clock, it's going to shift to the next stage. And then it's going to shift to that stage. So instead of toggling or counting, it's just shifting the pulse through. It's a very common thing that you use when you get complicated digital logic to generate selections on multiplexers and things like that. Okay, I threw in a pulse width modulator, which isn't exactly digital, but it's one of the things that you use in the digital world to go from kind of analog to digital, where you're taking an analog signal, sine wave, triangle wave, and you're converting it to a pulse of varying width. And the width is proportional to the amplitude of the input signal. This is what you use to do a D-class amplifier. And then you can run this through a low-pass filter and get this waveform back. Because the area under the curve in these pulses, okay, is proportional to the amplitude of the signal. So when you basically integrate this out, you're going to get this original sine wave.
And filter is just going to be a LC circuit and a
Could be just a low pass filter, whatever. You basically want to get rid of all the harmonics on these square waves. So it just needs to be the cutoff frequency a little bit higher than whatever the fundamental is that you're trying to get. We also have comparators where we compare two analog values and generate a binary output, a 1 or a 0, depending on whether it's above or below the comparator. You see that a lot in like switching power regulators and things where they're comparing a value. A number of places to choose. So in this case, it's set up for whenever this input signal exceeds 4 volts, which is what it's starting out on this waveform, it's going to go true. And it's going to go false again when it gets to a lower value, and there's some hysteresis in it, which is why it goes off at a lower value than what it triggers at.
So would they use something similar to that when someone has grid tied solar to make sure that they're in phase with the grid system they're tied to, or
Possibly. Anytime you need to compare a signal to a fixed voltage on whether it's above or below. And that's the information it tells you, that you've crossed that threshold. Now, it could go up to 5 or 6 volts, but it's telling you that it crossed the 4-volt threshold in this case. And this doesn't have to be fixed. I mean, you can have that as a variable, depending on what you're looking for in the circuit. That 555 multivibrator that we looked at before, has a comparator in it for the trigger. And that's how it determines when the capacitor is charged up to that trigger value. Okay, now we also have analog to digital converters and digital to analog converters, which we saw in the software-defined radio. So in an A to D, okay, you normally have what's called an analog sample and hold, where it can capture an analog value and hold it. It charges up capacitor. And that signal is fed into the analog to digital converter, which will generate a digital signal that represents the value of the analog signal. So if we had, in this case, we got a really simple 4-bit, so it can represent 16 values. So let's say, really crude one, say it worked at 16 volts. So if I had a 16 volt signal coming in, then the output is going to be 1, 1, 1, 1. If I had a 1 volt signal in, it's going to be 1, 0, 0, 0. So whatever it is, depending on the number of bits, which determines the range.
So you still have just a amplitude in the bits, and then your clock is going to do the frequency or the sampling rate?
Yes, on how fast you sample it. So every sample, like if you're doing an RF waveform, if you're sampling at a gigahertz, let's say, then you get that digital sample, and then you get the next one. So in the SDR, you've got to look at more than one sample to process a filter or something like that. You can't just take a single point. Now, with a single sample, you could amplify it, or you could divide it, reduce it. But to do filtering, and normally you'll do a quadrature also. You do 2 of them, and you get one 90 degrees out of phase with the other, so you can do the processing. And we're not going to go into that kind of detail, because I don't understand all of it that much either.
And then all the function of a DSP or something.
You can actually, they use DSPs to do some of this. Yeah. And most DSPs have a analog to digital input, maybe more than one. Now, you do just the opposite with the D to A, where we're going to feed a digital signal in and generate an analog signal out. And a lot of times that's as simple as a resistor network. And you just filter it with a low-pass filter and get the original analog signal. I thought I had an example where I tried to make one of those, but if you do a resistor network where they're representing the binary values, so you've got one resistor tied in, the next one is going to be half the voltage, would be twice the value. The next one is going to be twice that, and the separation between them is based on the
ESP32. I haven't heard of that one.
It's fairly new, and it's really a little microcontroller. I don't know much about it either. Really?
Somewhere in the back of my mind.
Okay, well, Arduinos made by a company in Italy, been out for a long time. They're mostly used in things like 3D printers. Most 3D printers were based on Arduinos, and there's different versions of it in the family. It's a microcontroller, and and you can program most of these in Python or some other languages. They allow you to do bit manipulations. So they'll bring out these, in this case, these digital I/O pins, which you can set them up to be a digital input or a digital output, depending on what you need. You can set them either way. Huh? This is pins 2 through 13 on this. So there's 11 of them. You have a serial in and a serial out that you can use to do RS-232 or things like that, RS-485. This has 6 analog inputs. So they go to A to D converters. Some other things like you can connect it to USB. Here's your, oh, they spelled that wrong. I didn't do that. Your analog reference for the A to D converters. Because those when you build those A to D converters, they will actually have comparators internal to them. So that's what the reference is for. So they're used a lot in as embedded controllers in a lot of things. Like I said, 3D printers, stuff like that. Most of them I'm familiar with have been in 3D printers. They're fairly cheap. Currently, it looks like there's some other variation, but this is the main. And it started with the Arduino Uno, which is one of the smaller ones and cheaper ones. Then they came out with a Nano, which is even smaller. It's really for real embedded stuff. It's about the size of this one. You can take it out. Then there's the Arduino Dewey, which is really a full-blown, almost computer. It's got a lot more I/O pins, pulse width modulators, more analog in and out. We got more RAM and ROM. That's a Raspberry Zero. That's about equivalent to the Arduino Nano. And then there's the Mega version of the Arduino, which has more I/O and things. It's used in higher end stuff where you need more processing power. Now, they also came up with what they call shields. And these are boards that plug on to those headers on the base board and allow you to do things like control motors. See, this one has accelerometers and a gyroscope and stuff, which things like, remember what was that two-wheeled thing people used to ride around on that was very popular?
Segway.
Yeah. You use something like that in a Segway, okay, to be able to control it, because you have to sense acceleration and direction.
When these things have big heat sinks on them?
No.
No?
Well, I mean, when you're actually getting to controlling a motor, yeah, the motor controller may. This would generate the control signal for it, but you may have to have a motor driver external to that, depending on what kind of power you're talking about. You can get them, connected to the Ethernet. Now, a lot of these others, like Raspberry, most of them have Ethernet built in, so you don't have to do an add-on board for that. There's relay shields. You get a whole bunch of relays you can control. There's just dozens and dozens of shields. These are ones actually produced by Arduino, the company, but there's third-party companies that make dozens of them. Adafruit, SparkFun. Those are probably the
9
biggest ones.
axis,
Huh?
9 axis? Or is that just a model?
For which?
Arduino 9 axis motion shield?
Yeah,
I don't think it's the 9
sure.
getting to the axis.
Yeah, I'm trying to figure that out.
X-
It's got like a model of joints. Yeah.
X, Y, Z, A, B, C, U, V, W. Yeah. U, V, W are coaxial with X, Y, and Z. A, B,
Okay.
and C are rotary.
Wow. Oh, so my brother probably knows about that stuff because he does the,
Well, I was into CNC,
okay.
and you can do 9 axes on a milling machine.
Wow.
Okay. Raspberry Pis, British company. Exactly how they pick pie, I don't know, but they have pie pans, pie hats, pie plates, all kinds of pie things. In the case of a shield, they have a hat, okay, which we'll talk about on the next one. The Raspberry Pis, the larger models, are essentially a full computer. Normally running a version of Linux with video, audio, microphone, USB, wireless, Ethernet, the whole 9 yards. You plug in a monitor and a mouse and a keyboard, and you can be on the air with one.
About stuff you should pay attention.
Yeah,
Oh,
and they're quite amazing, very popular. They use the ARM chip, which is the same family of chip that you've probably got in your cell phone. Apple started using them. I believe they're in Androids too. And there's a whole
like a Qualcomm deal or something like that.
there's a whole family of ARM processor chips. They keep coming out with new ones. Some of the hats that you can get. Excuse me, we're not to the hat yet. The variations, they came out with a Pico, which is the smallest one, which is even smaller than the Zero I showed you. And it has less power, but for some simple things, it's more than enough. The Zero has enough processing power to do a hotspot for digital voice with D-Star, DMR, or Fusion. The latest version of the Zero, which I'm trying to get, is the 2W, which means it's wireless. Raspberry Pi anythings have been impossible almost to get for the last over a year.
is this the source from China?
Well, kind of, because
Amazon
even
stuff.
though it's British, the chips are fabricated in China.
And that brings our conversation the other day. There's a guy who's into keeping, security in your communication, cell phone, that stuff. And he was using some of these Pi stuff to build some of his, routers and things like that. But being he's, doing stuff commercially, he's given up and decided just to use a NUC. Because a little, IBM, NUCs, they're easy to get. He's not having to wait 3 months, 6 months to get a handful. And he just buys a lower powered NUC. He doesn't need full power duct and he can get them all day long. And they aren't that much more expensive.
It was something I got last week, talked about that and the fact, and actually it was from, I think the chairman, CEO or whatever of the Raspberry Pi company. They had been predicting availability for the general public this coming December. It'll be almost 2 years. But apparently things are freeing up, so you may see them sooner. And you can, if you go to some of these sites like Pi Shop, Adafruit, SparkFun, a bunch of those, newer, you can have them notify you when they get them in stock. And they'll get a handful in stock. And if you're quick enough, you can get one, which is how I got this. Because I was quick enough that time. But I understand it's not that they're not making any. The ones that they're making are 90-something% are going to companies that use them in embedded products, large manufacturers, where you don't even know there's a Pi in there. So they're getting them. Individuals almost can't get them. And if you were a company wanting to do it, you might be able to negotiate something, but it might be too late.
Yeah, I think he's buying batches like 50 or 60 at a time. So he's not doing really large batches.
Yeah. Of the regular Raspberry Pi, it's gone through the first Pi, like the 1, the 2, the 3, now the 4. And in most of those, they've had a version A and a version B. I've heard there's going to be a Pi 5. I'm not sure when. The Pi 4B is currently probably the most powerful one they have, and it comes with, you can get them with up to 8 gigabytes of RAM on it. The 8 gigabyte one is $100. No, $75 if you could buy one. Now you can buy them off of eBay or Amazon, and they go for 200 plus, and they're probably used. Now there's also this Pi 400, which I'm not familiar if this is a different board or it's the one in the Pi 400 that they sell. In which case, I have one and didn't know it.
Slow it down.
Yeah. And it has a 1 gig RAM and board. Oh, slot.
I also snagged this.
I
That's a
think
Pi 400.
it's 1 gig on board and just
Yeah,
Yeah. Yeah.
huge.
And I thought that one had more than 1 gig in it.
So
But-
Bob, they do have the 4Bs on Amazon. I was recently looking at one as a ADS-B receiver. So they do have them back in stock, but I don't think they have the 8 gig ones in stock.
Oh, okay. Who was that had them?
Amazon.
Oh, Amazon.
Yeah, and they're new.
What are they selling them? What are they selling them for?
About $119.
How much?
119.
Okay, well, the list price for the 4B is 75.
Right.
And if you can snag one off of Newark or one of the places, you have them notify you when they're in stock, and if you're quick enough, you can get them for the list prices. In fact, I only paid $100 for my Pi 400, which is what it lists for. It brings out all the signals, so you can
Plug in.
do other stuff with it.
Don't know what the hold is on that.
I think that might be one of those Kensington security
Oh,
strap
okay.
things. I'm
Yeah,
not sure.
that makes sense, because I don't see.
Yeah. Little pinch down,
Yeah.
this stuff is crazy.
Okay. And in the Raspberry world, we have hats as opposed to shields. These are just some of them that are available from Raspberry Pi. Again, there's third parties that make tons of these things for anything you can think of. There's a stepper motor hat, which will drive two stepper motors that you can use for, like, if you wanted to build an antenna controller to track it, for satellites or something with azimuth and elevation with a couple stepper motors, you can do it with this and a little bit of programming. See, the Pi step is 4, is similar to that one. I guess the basic difference on the Pi step 2, it's working with unipolar stepper, which are the smaller ones that uses 5 wires instead of the 4 wires on the bipolar.
So stepper motors, what are some common number of steps on a rotation?
200 degrees typically.
200 degrees.
200 steps per rotation.
200 per.
Now you can get them at 400.
Okay. And
So it's either 1.8 degrees or 0.9 degrees.
okay. Now for amateur radio sub-point antennas, that's generally.
Yeah.
Plenty.
And with a microstepping controller, you can divide that again by
30 seconds.
They say up to 30. Well, it doesn't work very good
Yeah.
above 8, but 8, you can go 8 microsteps and you lose some torque. So if you have much back torque on it, I mean, it could slip part of a step, but
If your antenna has that much gain in that directional.
yeah. If you balance the wind load on your Yagi, so yeah. There's a little pan and tilt hat I thought was kind of cute. It's fairly cheap. I might get one to play with. And you can put a camera on it, pan and tilt it. The Sense hat is kind of cool. The European Space Agency built a thing called AstroPi, which a friend of mine did a version of it with 3D printed the box for it. And this has a LED display matrix on the top. It has accelerometers, gyro, humidity, temperature, magnetometer, a couple other things all in this one board. And they developed it for the astronauts on the space station to go play with. And it's a little, not very big box. It was kind of cool. Okay, you probably never heard of a BeagleBone.
That's one of Steve's favorites.
Oh, really? I didn't know he knew about a BeagleBone.
Yeah.
I'll have to talk to him. Well, I gave Bruce one yesterday.
Okay.
The BeagleBone Black was sort of the entry one that was the beginning. It again uses the ARM chipset, similar to what's in the cell phones and things. The interesting thing and why this was very popular for CNC is it has what they call 2 programmable real-time units, which are 200 megahertz sort of RISC processors on it, in addition to the main CPU. And they can run independently and talk through shared memory. So you can set them up to generate the stepper waveforms to drive motors. Instead of having to do it in software, it's actually done in the microcontroller PRU. So they can easily generate 1 microsecond steps.
Wow.
And it's, like I said, it's independent of the other processor, which is running your path algorithm and things like that, plus driving a display for the human interface and concurrently. And there's 2 of them. I've only used 1, and I could generate 4 axes and read an encoder for jogging. These are more like the Raspberry, where it's more of a full-blown computer, where you've got HDMI, Ethernet, everything you need, and it runs Linux. The family is the black is the that was really the first one I was aware of and the lowest cost. There's the BeagleBone green, which everybody had to get on the green thing. The big difference is on the green, it has Grove connectors. It's a bunch of sensors, mostly sensors, that all have a common format plug and a protocol. So on a lot of these boards, you can get a Grove interface and plug these standard sensors into it for temperature, humidity, accelerometer, all kinds of stuff like that. And then there's some control, for relays and it's just a whole family of things for hobbyists and makers. Okay. So, and you can prototype stuff using those sensors. It's really, you just plug them in, easy to use. This one was new to me, the AI 64. I was going to investigate. It sounds like it's probably expensive because the description here is impressive. I'd say that's a full-blown computer, and it still has, actually, I think this has 2 6-core proofs on it. No, those are the real-time units, the processors, independent processors. I'm not sure what frequency those are running at. On the black, they're 200 megahertz. It's got more codecs on it. It's interesting sounding board. And again, we have add-ons. In this case, they're called capes because of Peanuts. The dog in Peanuts wears his cape. He's the beagle. That's where the BeagleBone thing came from. And there's a communication cape that lets you do all kinds of COM interfaces, old current loops. I wonder if anything uses a current loop anymore. That used to be teletype. RS-485, a CAN bus. Yeah.
Okay.
They have a load cape, which will let you do relays and motors and high current devices like LEDs. The motor cape, which is a pulse width modulator motor control. That's one of the ways you control a DC motor is with a pulse modulated signal. So the speed of it is going to be proportional to the width of the pulse. And then the power cape, which let you interface it to other voltages. One of the things I didn't mention, the Arduino's interfaces are mostly 5 volts. So it's very easy to interface it with standard TTL logic. The other ones tend to be 3.3 volts, so you need to do some level conversion in a lot of cases. And I think that's what this one does, is some of the level conversion, so you can interface it to 5 volts easier than having to do separate little level converters.
Up to 30 ampere.
Huh?
It says it can handle up to 30-volt input.
Yeah.
Probably gets a little bit warmer.
Yeah.
Any questions on digitals? That was kind of an overview, and we didn't go very deep.
Yeah. So most of those usually run on some sort of Linux flavor.
Yes. And there's a lot of variations, but yeah. The Raspberry Pis run on Raspbian, which is their version of Debian, which is one of the main Linux distributions. I forgot what's running on. Well, I don't know there's that many, but yeah, there's a few. Yeah. And there's variations of variations. Because they're like Ubuntu, and there's a bunch of different Ubuntus. There's an education Ubuntu and something else Ubuntu. Yeah. But there's, basically they're all the same. I mean, if you know Linux, it's not there'll be a few little things that are different. The way you handle packages, something like that varies between them a little bit. I've mostly used variations of Debian. I had some Ubuntu stuff a long, long time ago. And I forgot what there was another big one that I can't remember. I can't remember a lot of things nowadays.
Well, I was running Ubuntu on a laptop for a while. And there was a fair amount of ham, apps that I could get for it.
Yeah.
Yeah, no, that's the other thing on the Raspberry Pis. There's, I forgot his name now. I get emails because I'm on the distribution. He created what's called HamPi. It's a Linux distribution that he modified, and it has a whole suite of ham applications. Yeah, to do different things like ham clock, which is a clock that shows the satellite stuff, the different time zones and all those things. The sunspot activity is part of it. Stuff for tracking satellites, a bunch of applications like that, all in one package that you can load and run on one of the Raspberries. I think he made a version to run on the PC, but I haven't tried it. Let's see. I have. How do I get back to my desktop?
Hit escape.
In
If you hit escape,
usually
it should bring it back.
escape.
Oh, escape?
Yep.
Nope.
Stop share, maybe.
Okay.
Yeah.
Oh, we see Aaron.
You're on the big screen.
Name's incognito.
Yep.
Witness.
All right. You ran them all off.
Okay, but now, always do that. I don't know how to get back to. the Zoom
I think you
screen.
ran off the rest of the, no, you didn't. Okay.
What's going on?
Return to the meeting.
It's not shooting on the bottom, so
Okay. Can you see that one, Aaron?
Yes.
Okay. I was going to go over some of the stuff I forgot to do in the first one. And we didn't talk very much about transformers on how they actually work. We mentioned mutual inductance. I don't think I explained it. And it's where, because they're on a common core, whether it's air or some ferrite material or iron or whatever, they share the same magnetic field, so that if you put a current through one of the windings, that magnetic field that's created causes a current or voltage in one of the other windings, and you can have more than two. And that's what's called mutual inductance. And from the impedance standpoint, you see the effect of both of them. Okay, depending on how many turns are on each side will determine what the inductance actually looks like. So as that field increases, it increases the voltage or current on the other winding that isn't directly powered. And I had my Lenz's law demonstration, which Aaron and Samantha won't be able to see, but I'll let Byron do it. We have a supermagnet and a piece of PVC pipe, and he's going to time how long it takes.
Yep.
That was quick. I'd say it's less than a second.
Okay.
Now we have a piece of 3/4 inch copper pipe, and he let it go, and he let it go, and it finally came out. So the question is, why did it take so long?
Yeah.
So what is that?
Only
10
5 seconds.
5
Yeah,
seconds.
yeah. I don't know.
It's because the
I
copper
can't
pipe
count that quick.
is acting like a one-turn coil that's shorted together. So as that magnetic field moves through that coil, it is creating a current that's creating an opposing magnetic field that's trying to prevent the magnet from falling, which is what happens in a transformer, basically. And if there was no losses, the magnet would be stationary. But because there's some loss in this real world, it allows one field stronger than the other. It allows the magnet to fall.
who's the guy that dropped the apple?
Newton.
Or he hasn't gone nuts on the rest of it.
That was Lenz, Lenz, a lot of the magnetic stuff.
So I suppose you could measure.
I tried,
Ooh.
and actually, I could only see it. I wrapped some wire around it, and I could only see it when it passed through the external coil.
What's that?
Huh?
As you dropped it through there, it created some polarity.
Yeah.
Yeah, so let's stop it through a few more times. See what it does.
Are you using the same top and bottom?
Yeah.
Yeah.
Slowing down.
Just so you guys know, they're playing with the magnet.
It is, it's slowing down.
This was an MIT demonstration. You can find it on YouTube. Okay, we talked a little about turns ratio on the transformers. And that's how it determines whether it's a 1-to-1 or a step up or step down, depending on the ratio of the turns. but it also affects the impedance. And the impedance of the transformer is going to be the square of the turns ratio. So where that becomes important is if you're trying to do a matching transformer for an antenna, you need to know what the impedance transformation ratio is. So it's the square of the turns. So if you wanted a 49-to-1 transformer, which you'd use on an end-fed half wave, you'd have a 7-to-1 turns ratio. And probably have something like 3 turns on the primary and 4 turns or 24 turns on the secondary, right?
For
Something like that.
yeah, for your 60-41. A lot of times they'll tell you that the crossover, if you're doing a crossover turn, that count that as a full turn. But if you measure it, it's actually less than a half turn. So that's something to think about too.
Okay. I always get confused on the turns and always have to go back and count them several times
Yeah, anytime.
and then add one or take one off because okay. Okay. We didn't talk a lot about AC waveforms, and there's a lot of other than sinusoidals. One of them is square waves, and we mentioned earlier about distortion and amplifiers, where you get flat topping or clipping, where it's starting to look like a square wave, and what effect that is. So the thing showing the basic 4 waveforms.
How you burn up your driver, your audio driver.
But also how you can recreate a square wave by adding up all of the odd harmonics in this series, where you take the third harmonic with an amplitude of 1/3 and the fifth as 1/5 and so on and so forth. And even, I mean, only doing that many, you can see how it's a square wave with ripple on the top. So the more additional harmonics that you put in there, that would eventually make that into a perfect square wave if you had an infinite number of harmonics. So when you have an amplifier and you're getting clipping, where your sine wave is starting to get this flat top, it means it's generating all these harmonics, which is why it's a bad thing.
Then your tweeter smells like the smoke ran out.
Okay. The other thing we didn't talk about was RMS. I think we might have mentioned it, but it's really a way of measuring the equivalent voltage or current of an AC waveform to a DC waveform. So the RMS value of a sinusoidal AC wave is the same value of heat generated by the equivalent DC voltage. So it's essentially the area under the curve. And the way you get there is taking the peak value of the AC wave, which is from 0 to its highest point, and multiplying that by the square root of 2. And that gives you the root mean square, or our close approximation to it. It turns out it can get complicated if there's any DC component to it where there's an offset. It turns out to be the square root of the AC RMS plus the square of the DC part. to get that result. I'd never dealt with that, but it does make sense. If you had just the peak to peak value, like if you looked at one of these plots or you looked at it on an oscilloscope, you need to take half of that to get the peak value and then multiply it by
That would be the mean.
by 1 over the square root of 2. Be 0.707 times the peak value. Here's an example of a nice sine wave. And we have our peak voltage and our peak to peak voltage. So this is actually equivalent to your AC power. So it's actually going to be around 270 volts peak to peak, even though you think it's 120, it's 120 volts RMS. So 0.707 times the peak value is going to wind up giving you that 120 volts, which says it would generate the same amount of heat or do the same amount of work as 120 volt DC.
So that makes RMS very useful.
Yeah, that's why you use it. And it works great on a sine wave. If you got others like a triangle wave, I think you have to use the square root of 3 or something, and it gets a lot more complicated. Fortunately, we tend to deal with sine waves. It's only those other waves when you're not doing something right. And here was the thing we never talked about, the house wiring, showing the normal setup where you have a distribution transformer out on a pole or maybe underground. If you're fortunate enough. I still have a power pole and a power line, which is too close to my antenna, but that's life.
The berry does about 2 years.
The feed coming into your house is going to be a 240 volt RMS signal that's center tapped, okay, with the and that's the neutral. As soon as that comes into your service panel, okay, it goes to a ground rod outside the house. You also have what's called the safety ground that's connected to that neutral at that point only. And that's will show up as your green wire in your house wiring. Whether it's 240 or 120, you're going to have a green wire. If it's a normal 120, which is most of what you're going to have, you're going to have a neutral or white wire and a black wire, which is the hot wire, and the safety ground. The purpose of the safety ground is it will be connected to any metal enclosure that is plugged in, so that if there's a short circuit from the hot side, okay, it gets shorted to the safety ground out to the ground outside instead of going through you. Nowadays, most things like your drills and all that kind of stuff are double insulated in plastic, but most of them still have a 3-wire cord, so they do have a safety ground in them. In the case of 240, you only have 2 hot leads for normal distribution, plus the safety ground. Now, if it's 240 going to a stove or a range, it will also have a neutral. So they get 120 plus 240 out of those 3 wires. My shop is wired that way with a neutral. So I have all the receptacles split. So one side of the receptacle is the black phase, the other side is the red phase, and they share a common neutral. So that if you've got stuff plugged into both of them, it reduces the current flow through the neutral because they're in opposite directions. So if it was perfectly balanced, you'd have no current flowing in the neutral.
So you can flip your one of your waveforms on 2 or 3.
Say what? Oh,
You could flip one of those
yeah.
to show it's out of phase.
Oh, yeah. But I didn't.
Yeah. I know it's gonna keep you up at night, but
But we can pretend.
yeah,
Okay, so here's see, what did I plot?
it looks like you're
doing it.
2-phase.
Yeah, that's the your 120 volt in, which is going up to about 170 volts. This is 100 and 200. So the peak to peak is going to be that, what was it, 270? Close to 300 volts. The oh yeah, this is the other phase.
Oh, I think someone told me that around here we run now what is 120 degree 3-phase.
Yeah, but this is not 3-phase. This is sort of, nobody calls it 2-phase, but with the
Yeah.
neutral, it's actually 2 phases that are 180 degrees apart. Whereas your 3-phase, you're 120 degrees. And if you were
Yeah.
4-phase, you'd be 90 degrees. You don't
But,
see much of the other phases, but most power stuff, big motors, power transmission is 3-phase. Because you have less current
Commercial buildings.
that way. Go ahead.
I said you'll see that more in commercial buildings than residential.
Yeah. Most people only have a 240 volt going to their dryer or to their stove. Don't normally have a 240 volt outlet unless they have it specifically put in. Or you have a 1500 watt power amplifier for your radio. You probably need 240.
So if you're 180 degrees 2-phase, it would be 240. But if you have a 3-phase system and you're running 2 phases of it, then you want 208 volts?
Yes,
Yeah.
I believe it's 208.
So there's also a 3-phase with what they call a wild leg or a bastard leg or whatever, where it's got 240 coming in and then it's got a 208 coming in as well.
Yeah.
Ooh, nice.
Plus, you can have it in a Y or a delta, which affects it too. That was many, many years ago in electrical machinery lab. Okay, and we didn't talk about power measurement. And you normally use a watt meter. In amateur radio, you're mostly concerned about the power going out to your antenna. So we use a directional watt meter that actually measures power in both directions. It can measure forward power going to the antenna and reflected power coming back. In a lot of cases, like in the picture shown, it's a cross needle display, and there's actually 2 meters in there, one over here in each corner, and reflected power drives one of them, forward power drives the other, and where they cross on these red lines on the chart shows you what the SWR value is for that. It's a complicated ratio of the reflected and the forward power. The other thing that we measure is peak envelope power. Like I show in the diagram, when you have a modulated carrier wave, okay, the peak envelope is the highest point of that envelope, not the average. Now, when you have an unmodulated carrier, the peak envelope power is the same as the average because there's no modulation. So they will be the same. Use that same value. That's a test question about the difference in the two. And I think the way they do the question is they give you an unmodulated carrier wave and want to know what the peak envelope power is. It's the same. We also have effective radiated power where you take, if I got this right, the peak envelope power and multiply it by the gain of your antenna system.
So much truth.
Well, they assume because when you have a high gain antenna, you're concentrating the power. I mean, the same power, you don't actually gain anything. You just redirect it like a flashlight. Okay, forward, reflects the beam forward. Well, if you didn't have the reflector there, the same power is coming out of the light. Okay, it's just you're concentrating the beam. And that's the way beam antennas work. So they figure in the antenna gain to get the effective radiated power. So if you had a 10 dB gain antenna, you get an additional 10 dB gain in power as far as ERP.
They haven't changed rules because it was the power that you're feeding to the antenna. At the antenna feed point is your 1500 watt limit, but your RF exposure is going to be your ERP.
Yes.
Okay.
Yes. ERP, yeah. Exposure, which apparently is something that's changing. I understand on the new general exam, there's more stuff going on with radiation exposure.
Which means I should probably file my.
Well, one of the things I guess they're going to insist on you actually keeping records of your calculated exposure. Before it seemed like it was something you should do. I think they're going to make it something you have to do. But it's easy. I mean, you just have to have it in your station log. And there's the ARRL site has a calculator and you just put in the numbers, what your power is, what your duty cycle is based on the type of modulation.
Yeah.
Well, for different frequencies. From 30 to 300 is worst case. It's 1 milliwatt per square meter for humans because your soft tissue like eyeballs and things are the most susceptible at those frequencies. And that's for a controlled environment. And then it's about half of that, I think, for an uncontrolled, which means your neighbor who doesn't know you're transmitting at them. So because they don't know it and stuff, you're not allowed to expose them to as much radiation. So you just plug in 4 or 5 numbers and it will tell you how far away you have to be within the permissible limit. And if you, for instance, do it on your walkie-talkie and do like 50%, well, I don't know if I did 50. If you definitely do it at 50% duty cycle, it says you need to hold that about 2 feet from your head. But I don't think, well, you're a lot lower power, but you could still go through the calculation. And since you got it right there, yeah. And they claim, some people used to work with a guy who put tinfoil on his head.
Oh, I thought those were aliens.
Oh, no, you could have, what's that? Colonel Jack Ripper from the Dr. Strangelove.
Oh, okay.
Only drink,
Yeah.
rainwater, distilled water.
You can also get these watt meters that have a digital display and will read out in forward and reverse and SWR in a digital display instead of trying to read the cross needles. Some people like those. I don't know. Mine's a digital one. Huh? Oh, yeah.
Keep your vital fluids.
Okay.
Bartering.
Anything I forgot to talk about?
Well, let's see. Oh, we haven't talked about KC2 UFO.
All right, talk about KC2 UFO.
So KC2 UFO is a call sign that Dave Slauson uses for his club. Or
Sky watchers or something.
Sky watchers and communicators. So KC, keep calling to UFOs. Yeah. And he has a club structure that was unfamiliar to the FCC, and they were not going to allow it until he talked to them.
Yeah.
And they decided to allow it. He has a king and queen. Okay. And on the solstice, the king and queen switch, which is he and his wife. And that's how they, determine who's leading the club. But
The FCC forms want you to put the president and the vice president.
yeah, yeah. And they hadn't had a king and queen before.
Yeah.
So generally, Dave is noted for being one of the funner amateur operators around here, as far as special events. Like we had permission to use Ray's Cassis's station for the Mayan end of the world war 2012 or whatever that was. And Ray has, big Collins gear and all that stuff. So that was a nice station to use. We would do special events over at the Veterans, museum for Memorial Day and Veterans Day.
I want to hear it. Volunteer.
Well, it depends upon the politics at the time and who's leading, and how you get along in that environment. But I understand for the most part, it's good. So he would do those type events. He became no fun and was working too much, but that has changed. So he's getting back in, and now he's doing parts on the air type stuff. So I don't know whether he's going to start doing other special events.
Does he do your QRP stuff?
Sometimes. Usually he's doing parts on the air.
Okay.
So I think he came out last time.
When you were at Kelly Park?
Yeah.
I didn't see him when I was there, but I was only there for a
Okay.
little bit.
Yeah.
Yes, Dave.
Awesome.
K4UZM. But he's also a contrarian. So if you want a contrary opinion during a club discussion, bring Dave in. So,
Not that Viren isn't.
yeah. Like, we're talking about doing D-Star. I think to most digital modes, but especially D-Star and Fusion, because you have the AMB codex that essentially makes it proprietary.
Right.
Okay. And which makes it encryption. Okay. So the French telecommunication union decided, well, being it's encryption, it's illegal and it shouldn't be here. But that's only, governing body that's done that. And then it's basically, it's a social media app that you can have on your phone, but you need an FCC license to use it. So how was that amateur radio?
Yeah.
Well, it's no different than IRLP. You need a license.
Yeah.
How did you brought up a whole different world for me all of a sudden? How do they treat VPNs?
Yeah, that's a good question.
Who? The FCC?
Uh, the Papa Network in what are they calling the?
There's an enterprise now that's new, that we just had to sign up to.
Well, they were taking some of the 5 gig privileges away from the amateurs.
Yeah.
And that was really screwing up a group called the Papa Network. But they had set up a lot of stuff in California for communication based on 5 gigahertz. And of course, with that much bandwidth, they could pass video for special events if they were monitoring walkathon, stuff like that. So that's caused a problem there. But here, it doesn't seem like that mesh network sort of is popular.
No.
Well, I don't see a whole lot of control factors on these VPNs either. Maybe I'm missing something.
Yeah. Everyone's relying on Spectrum or whoever to shoot their
Yeah. Everybody's getting one.
yeah.
Well, there's a lot of them out there, free and paid. I've been using Norton for years.
We just put in a whole new Dell server system and everything, and this enterprise VPN came up as a standard interface. I spent a couple hours on a Zoom call yesterday to Dell. That trigger always out.
I run into a lot of things that aren't compatible with it, and I'll have to turn it off in order to get to certain sites or things.
Well, I think that mesh networks are going to be more and more as we go.
But I almost always have it on when I'm buying something on the internet.
Secure layers thing.
Right. And it does, cut down on tracking you because, you could look like you're on a server over in, Turkey or someplace if you want. I mean, you can pick your endpoint. I don't know how much that helps, but supposedly it does. I think Google tracks you regardless.
Oh,
I bet you do and don't know it. Because most people use Google servers to do their, yeah.
Total control.
yeah. Steve has a good story. He had a HP laptop, I believe it was. But he got tired of the Windows update stuff. He had Windows 10.
Yeah.
And so, he figured out all the virtual links and that stuff off. He was successful. Yeah. And then about a month or so later, HP calls him, Mr. Luchek, do you still have your computer? Are you still using it? A few weeks later, he was turned back on.
Okay. Aaron and Sam, you got anything before I stop recording?
No, I'm good on my end.
Nope, I'm good.
Okay. Did you learn anything?
I probably learned more than I was expecting, and I'm going to still have to do a lot of reading.
Yeah, me too.
Yeah, well, in order to pass the exams, you got to do practice tests. It doesn't matter, whether you take courses or read the books, you got to do practice tests.
Yep. Yeah, used to. Do about 2 or 3 times a week for 10 or 15 minutes and you should be good.
If you get up to 90% or better, you're good.
Yeah.
I'm working on that.
You don't need to get 100. You just need to pass, which is 74%.
Yeah,
And
that's
there's
how
only 35 questions for technician in general. So,
21
I
questions
passed my
or whatever
FAA
it is.
exam. Haven't crashed a plane yet, so
say that again.
I said that's how I passed my FAA exams and didn't crash a plane yet, so I should be okay.
Okay.
There you go.
All right. Well, appreciate coming. Let me know if you need anything else. I guess we'll start the technician class next Saturday,
All right, sounds good.
same time, same place.
All right, thank you.
All right.
Thank you.
You too.